So we're going to go back and we're going to talk about this again, mostly because, one, we need a little bit more practice. I'm going to go over some of the homework problems, as well as that, two, I have technically not taught you everything we need to know about work. So we're going to go back. We're going to kind of break this down again about what it means between work, conservation of energy, and in particular systems, what we mean by a system. And hopefully it's going to make a bit more sense after this. I'm so sorry. I know this has been frustrating. Believe me, it's been frustrating for me too. So we're going to take a close look to start with at systems and conservation of energy. So a system is a portion of the universe in which we are studying the changes within. Real fancy thing. But when we are looking at a system, we want to include all the energies at work on or in our system. If I say my system is the entire universe, that's a lot of energy at work in there. There's a really cool, actually, physics theory that from the beginning, based on conservation of energy, that from the very beginning of our universe, all of the energy was created. And we still have that exact same energy today. If we say our entire system is the universe, well, based on conservation of energy, all of that energy should still be there. It's a really interesting concept. You should check it out and read more about it. Now, when we're looking at a smaller system, like if I'm just looking at a book on a table, that's a little system right there. If I say the book on the table and then the gravity of Earth, that's another system. Separate from just book on table, we have book on table, and we're including the Earth's gravity in that. So we don't necessarily have to do this. In the textbook, they don't necessarily include every single force at work. However, we then have to address that there is like an outside God force just acting on our system. We're kind of like pretending it's not there, but somehow this energy is entering our system externally. And that complicates things. We can't look at conservation of energy the same way if we're ignoring that energy is actually coming into our system. So again, if I'm looking at just this water bottle, for example, and this water bottle, all my system is just this water bottle and gravity and the friction from the table. We could say that. If I start to push it and I pretend that my hand is not in the system, energy is entering this system, and the conservation gets kind of tricky from there. So what we have to do is we have to address the fact that, yes, on this water bottle, we have friction of the table, we have gravity pulling down on it, as well as my external force of my hand. If we do not include my hand in the system, things get kind of tricky, and that's how some of the questions are addressed in the textbook. So we're going to simplify it. So why do we want to simplify this? Why do we want to include all possible forces that work in our system? That's because based on conservation of energy, if we look at all forces, including any external, we're going to talk about this in a bit, the energy in the system final equals the energy in the system initial. This is true, again, only if we take into account all forces at play. So we will show that in just a second, knowing that the change in energy equals, you might have forgotten this, but change in energy equals work, right? That's the work energy theorem. Work equals change in energy. That energy does not change if we include all possible energies at work, which means if the energy does not change, what would work equal? 0. There we go. But this only works as long as you include all energies in the system. So this is a little bit different than what I had said before. What I had said before is if we start and then stop, it's 0. What we need to think now is as long as we address all energies in the system, work is going to be 0. Again, there's a way to look at this where if you don't include all of the energies, work does not equal 0, but it makes it a lot simpler. If we include everything, work will equal 0. So in all cases from here on out, guys, when we're doing these questions, we're going to set work equal to 0 as long as we include all the energies. Now, with that in mind, Oh, I meant to put this here, I think. Yes, sorry, I got this switched up. There we go. So we talked yesterday about different types of energies. There is one more I actually need to include in order to address problems this way. And that's why I was getting a little mixed up yesterday, because I didn't include this one. And then we weren't able to address the problems the way I wanted to. The last force, if you want to add this to the list from yesterday's notes, is an external energy. So we talked about internal energy, which is, again, friction in particular, or air drag or chemical reactions in your body, if we're talking about a person actually doing work. But we didn't talk about if there is some outside force pushing an object. There was a question like this that we're going to look at for C, where there was some external force pushing an object. And I didn't really teach you in a way that allowed you to do this question like the others. So if it's external energy, that is calculated by the work done by external forces, and work is just force times distance. So if this is just an applied force pushing an object a distance, we can calculate that by doing force times distance. Now, going back to what we talked about yesterday, given all possible energies, we have 5 now. We had the 4 from yesterday, and now we're adding on a possible external. We can expand energy final equals energy initial into this. Kinetic final plus gravitational final plus spring final plus internal final plus external final equals, what are all of my energies internal? Go ahead and write it down. So expanding this out, this equals K initial plus gravitational initial plus spring initial plus E internal, I'm not going to do the whole thing, initial, plus E external initial. Now, when we're doing a question, we have to understand that not all of these energies will be at play, so we only need to use the ones that are at play. So going from here, here's how we get that from this, that the change in energy equals work, and that if we include all of the energies, work is going to equal 0. So moving everything over to one side and reorganizing, what we get is this. If I move everything over, I'm going to go ahead and take all my initials and move them over, right? So I'm going to reorganize this because it makes sense to put our energies together. K final, I'm going to subtract over K initial. This should look familiar. Gravitational initial, I'm going to subtract that over. So plus final minus initial. Go ahead and keep going with this and then click continue when you're ready. Okay, so I'm going to finish this up as well, actually. So we've got spring final minus spring initial plus E internal final minus E, I'm running out of space here, internal initial. And then obviously the last thing as well for the external, E external, I'm going to just put E there, excuse me, final minus E external initial. So obviously what this means, one more thing here, since I've moved everything over to one side, if I've subtracted all of the right side over, this equals 0. We have moved all of this side over. So all of these changes, this is the change in K, plus the change in the gravitational, plus the change in the spring, plus the change, equals 0. That's how we get to this, that the change in all of these energies equals 0, which is work. That's more what I meant to put right there. We know that the change in energy equals work, and so this shows us that as long as we include all the energies, work equals 0. We move everything over to one side, and it ends up equaling 0. Now, there are some questions which we're going to look at where you want to find the work done by just the external or internal forces. If that's the case, we're still going to say work equals 0. What we end up solving for actually is the change in E external, so you would solve for this, or the change in E internal, whichever one they ask you to solve for. So again, in that case, a simpler way to address it is to say that the total work in the system is 0, and then we can actually just find the change in external or the change in internal. So to sum up here, there's one more thing we need to address, and then we're going to go back and look at those problems from the homework. So if energy is conserved, there are some questions that ask about non-conservative forces. How do we address that? If energy is conserved, what does it mean by non-conservative forces? Now, non-conservative forces refers to energies that dissipate. So it doesn't necessarily mean that they aren't conserved in the sense they dissipate, like, we'll go on from here actually, like surface friction, which again we know generates heat. If you rub your hands together, some of the energy in that system here between my two hands is going to go into heat, and that energy just dissipates, right? We got this heat, and then once you let your hands go, eventually they cool off, right? That heat is dissipating. As well as also air drag. This also causes heat, which is why when the space shuttles re-enter the Earth's atmosphere, it gets really hot. That's one of the reasons why, because they're going so fast that they're generating a lot of heat from that air drag. And lastly, bodily energy. So again, this is like chemical or thermal, where if I'm actually doing something, I am exerting energy as well. This does cause heat in your muscles. And that's how that energy gets dissipated. Now, even though they, again, dissipate, the total energy still remains the same if we include them in the system. So I have all of my energy. The non-conservative goes away so that, yes, if we were looking at the final energy, technically, it'd be less. So, for example, again, if I'm sliding this water bottle across a table, I have my starting energy, yeah? Because there is friction involved, technically, my ending energy will be less. However, if we add in the energy that got dissipated from friction and from heat, that total energy is still the same. Basically, what energy conservation really means is that energy cannot be created out of thin air or disappear out of thin air. There has to be a cause. So if there is no external cause, if there's no friction, if there's no air drag, no chemical release inside your body, whatever, yes, from beginning to end, the energy is going to be the same. If there is an external or internal cause of loss of energy, it's not, if we still include it in the system, the total still remains the same. It's not just disappearing out of thin air. The exact amount that is taken, if I put it back in the system, the totals are still equal from beginning to end. Energy, again, cannot just be created out of thin air or disappear out of thin air. So that's what it means by non-conservative forces. We are still going to include them in our total. As long as we do that, we can still say work is 0. So let's go ahead and look back to these questions and try and look at them in this light. So this is your homework. So if you were unable to get these questions, do them now for your homework so that you can get that submitted. If not, just follow along again, try it again. Don't look at your homework and just see if you remember how to do this. So an 18-kilogram suitcase falls from a hot air balloon that is at rest at a height of 385 meters above the surface of the Earth. The suitcase reaches the speed of 30 meters per second just before it hits the ground. Calculate the change in internal energy of the system. So what they are telling us is there is a change in internal energy of the system. So we need to include that in our total. This thing is dropping. What do we think the change in internal energy is caused by? Air drag. The air is dragging up against this suitcase. that causes a change in internal energy. So as long as we include every force, if there's an external force or energy in the system, work is going to equal 0. So we have the total work equals, write out there's 3 total changes in energy in the system. Because we have speed, we have change in K. Because we're dropping something and we have gravity at play, we have change in U gravitational. That's potential energy gravitational. Plus, it tells us there is a change in the internal energy of the system. Now again, because we include this, we are going to be able to say that work equals 0. So I'm going to go ahead and expand this out. We're going to do what we did yesterday, figure out which ones are going to be 0, and then go from there. This is our end goal. We do not have to replace this with anything because we want to find specifically this. We're not going to replace that with anything. We might need to in another question, but to start with, we'll leave that. So let's expand this out. We got work equals, change in K is K final minus K initial, plus change in U gravitational is UG final minus UG initial, plus our end goal is to find what energy is going to end up being dissipated of our total energy, how much is going to get lost, right? So go ahead, read the question if you need to draw a diagram. Which we have 1, 2, 3, 4, 5, and not this because we're trying to find this, so that's not 0. Which one of these is going to be 0? Go ahead and give it a shot. Okay, so we know that as long as I include all energies in the system, I can say that work equals 0. We have a starting speed of 0 and a final speed of 30 meters per second. So that means that we do have a K final because we have a final speed. We do not have a K initial. If your speed is 0 to start with, you have no kinetic energy to start. Plus, we have a starting height of 385 and a final height of 0. So what that means is our gravitational potential will be 0 minus we will have potential to start. Notice this will happen, guys. We've talked about how kinetic energy and potential energy switches. I do have final kinetic energy. I only have initial potential. That switches, yeah? Plus the change in E internal. So from here, we're going to go ahead and replace what we have, our kinetic and our potential with the formulas, plug in and solve, and that's it. We're going to solve for change in energy internal. So I'm going to go ahead and rewrite with the formulas, and then I'm going to give you a moment to try it. So this is 1/2 mv final squared. I was going to say plus, but be careful here. We need to say minus because this is minus UGI. So mgh initial plus the change in E internal. So go ahead. I'll scroll back up to the question if you need to. Plug in all our information and solve for change in E internal. Okay, so our mass is 18. We've got 0 equals 1/2. Mass is 18. Our final speed is 30 squared. Minus our mass is 18. Our gravity is 10. Our initial height was 385. Plus change in E internal. Good Lord. Okay, so let's simplify this out. We got 0.5 times 18 times 30 squared minus 18 times 10 times 385. Ah, dang it. Go back. Plugged in divide instead of multiply there on accident. Okay, we should get Let me actually do this. I'm sorry, guys. For the purpose of matching the answers in the textbook, I'm going to go ahead and put that as 9.8, just so we don't get confused on why we're off by a little bit. Okay, so this comes out to be 0 equals negative 59814 plus change in E internal. So we can add over the 59814 to both sides, and there we have the change in internal energy. So this is the energy that is going to be dissipated because of that air drag. What ends up happening is, because this energy gets dissipated, if we ignored air drag, we would end up with a greater speed. But because there is air drag, the speed is actually less than it would be if there was no air drag. Hopefully that makes sense. We should know that in a vacuum, if you drop something, it's going to drop a lot faster than dropping something not in a vacuum, because there is air drag involved. So that's what this is saying. If we did this problem pretending there was no air drag, what would end up happening is, again, we'd actually end up with a greater final speed. Because some of the energy is lost to air drag, this speed actually is less than it could be. So let's try this one. I'm going to go ahead and actually set this one up for you. This is the other number 2. These are actually done the exact same way, almost. Whoops, I didn't address this here. Sorry. This looks confusing. There we go. There's one little thing we have to be careful about here, in that we need to know the height of the incline. But that's just a little bit of trig. So read this question, and then we'll go from here. So this question says, how much work was done by non-conservative forces? So we talked about, if we're trying to find non-conservative forces, we're talking about internal energy. So this is like friction, this is like heat. We can see that this person is sliding down a slope. So the non-conservative forces is friction. Friction is going to rub up against the skier and cause it to heat up, and that energy is going to dissipate. So we need to include that when we do our total work. So we are going to have to include the energy internal. That's the non-conservative forces they're talking about. Go ahead and write out the other energies at play here. Okay, we have kinetic because we're moving. We have gravitational potential. And again, we have that change in E internal. This is what we're trying to find. Again, we said that on the last slide. If we want to find the work done by internal forces, we're finding the change in internal. Okay, so from here, go ahead and take a moment to expand this, figure out what things are going to be 0, and then we'll go from here. Okay, so we got work equals, I'll expand this. We got K final minus K initial plus U final minus U initial. Put G there to be clear. Plus, again, we're trying to find this, so I'm not going to replace it with anything. This is our goal. The work done by non-conservative forces is this. So what things are going to be 0? Well, work is going to be 0 because we are including all forces at work. We have kinetic from speed, gravitational potential from height, and then it tells us there are some non-conservative forces at work, so we add those in too. So starting from rest, we are skiing down a slope of 40 degrees. The slope is 8 times 10 squared meters long. Excuse me, that's 800. Move it over 2. So we are starting up here and going down. So think about again, where we are starting from to where we end up, what that means for which kinetic energies are going to be 0 and which potential energies are going to be 0. Okay, so hopefully we're getting this. Starting from rest means an initial speed of 0. So we have K final. We do not have K initial. We're starting at the top and coming down. We start here. This is our initial height. We're going to need to find that, by the way. And our final height is 0. So we have 0 minus UGI. Notice how that works out very often. E internal. Okay, so go from here. Same thing. I'm going to give you a hint. You're going to have to do some trig. When we replace with the formulas here, I'll actually do it real quick. When we replace with the formulas, we need to know the height. You do not know the height. We know the length of the ramp. This is our height. So take a moment and try it. Okay, so I'm going to go ahead and do the height real quick, actually off of here. This is our triangle. We got 800. We've got 40. This is our height. So that's going to be sine 40 equals h over 800. So multiply the 800 over. I believe you had an h of 514. I'll just double check real quick. Okay, yeah, so 514.23 we'll say. So that's going to be our height that we plug into this formula here. Excuse me, I almost left off. I can't do that. We can't leave this off. Okay, so let's plug in. We got 0 equals 1/2. The mass is 75. The final speed is 20.2. Minus the mass is 75. Gravity, again, I'm going to go ahead and still use 9.8 so that we're getting the answer that's on the textbook. And the height was the 514.23 plus change in energy internal. This is what we're trying to find. So if you haven't already done so, go ahead and solve. Okay, so we got 0.5 times 75 times 20.2 squared minus 75 times 9.8 times 514.23. We get 0 equals negative 362,657.55 plus the change in energy internal. So again, we're going to add this over. We get that the change in energy internal, which again, this equals the work done by non-conservative forces, friction in this case, equals 362,657.55 joules. Again, this is the energy that will be dissipated. We started with this extra energy. We started with all my possible kinetic energy plus all that potential energy. But this is going to get dissipated by the end due to friction. Again, the total energy when we include it is the same, but this energy by the end will have been lost to heat. As long as we include it, though, the total is the same, and we can say work is 0. So trying this last one here. So this is one where we had an external force, and this is where, again, I hadn't talked about external forces, and we need to do that here. So the question said, treat the box on Earth as a system upon which the external force is exerted. So what this means is that we're going to include the external force in our system. So we have work equals, with this box going up a ramp. What are all of our energies we have present here? We've got kinetic because it's moving. We've got potential gravitational because we have a height, plus change in E external. We have an external force at work. So we need to actually, some God force, something is pushing on it. If we include that God force in the system, we're just going to add it to our total work. Now it says we want to evaluate the numerical value of the work. What they're saying is the work done by the external force. So we are still trying to find this. I want you guys to go from here and try this whole question. Because we have included all of the forces at play, there's no internal, because they say the friction force is negligible. So no friction, no loss of internal energy. We do have this external force exerted. Try and go from here. What is 0? Expand it out. Plug in the numbers, go from there. Okay, so we are trying to find this still, because again, this is the work done by the external force. This is the work done by kinetic energy. This is the work done by potential. All together, that's all of our work, and it equals 0. So we have that work equals K final minus K initial plus UG final minus UG initial plus we're trying to find the change in energy external. This is the work done by the external force. So work is 0. We're allowed to say that because we've included all of the energies at work in the system. Careful with this one here. This question did say we are moving at a constant speed. What that means is the change in K equals 0. If we are at a constant speed, I don't know what K final and K initial is, but I know that they're going to be the same. If I'm moving at a constant speed, my final speed is the same as my initial speed. Therefore, the change is 0. So we're going to replace all of that with 0. However, my potential energy, we're starting down here and we end up here. We're starting down here and we end up here. This one is different than the skiing one. Hopefully you caught this. That it's our initial where we have 0 because we're starting at the bottom. It's our final where we have the potential. So if you messed up, keep going from here, fix it, solve for change in E external. Okay, so we got 0 equals, we've got UGF, which is MGH plus, final, I guess I should say, change in E external. So the mass is 3.5 kilograms, right? Gravity, again, I'm going to still use 9.8. So it matches what's in the textbook. The height is 3 plus change in energy external. So 3.5 times 9.8 times 3. We get 102.9 plus change in E external. So we can subtract now the 102.9 over. Change in E external equals negative 102.9 joules. And in the textbook, I think it said 103. So the reason why this is negative here is because this is an external force. What we're saying is this was applied. That energy, negative. We can think about this as a negative. Notice again, the internal force was positive. It seems a little bit weird because we're thinking that the internal is being lost, whereas this is being gained. But because we're talking about the change, it works a little bit differently. The final minus the initial would end up being negative. So we can leave it as a negative. It's okay to put it as a positive as well. That's our change. That's our outside force doing work. So I hope this helps. I know this was kind of long, but I really wanted to make sure we were good with this. I needed to reteach it in a different way than I had been, so I hope this really helps.